Section 8.5 is going to get into the binomial theorem and Pascal's triangle. And what Pascal's triangle and the binomial theorem are going to allow us to do are quickly come up with expansions of binomials. So here the binomial x plus y quantity squared. The way you would expand that is you would do your x plus y times x plus y, since it's a quantity squared, and then you would FOIL everything out. So x squared plus xy plus yx plus y squared, which gives me x squared plus 2xy plus y squared. Couple things that emerge as you continue to look at these different expansions. The first thing that you see is that the number of terms we're going to have is one more than the power that I start with. So here, a squared 2, I'm going to end with 3 terms. The second thing you're going to see is that there is a pattern of numbers that appear in the front. In this case, 1, 2, and 1. The third thing you're going to realize is that as I look at the different powers of my first variable or my first term, they're going to decrease in a pattern. So here, x squared, x to the first, and then finally the last one has x to the 0 x's. The next thing you're going to see is that your last term's variable is going to increase as you go from left to right. So here we had 0 y's, 1 y, and finally 2 y's. And that pattern is going to hold throughout this process of binomial theorem and Pascal's triangle of expansion. Question is, where do some of those things come from? So the first thing we've got right here is all the patterns for the binomial a plus b raised to the n can be summed up in these 5 points, sort of what I've already talked about. There's n plus 1 terms, so there's one more term than the exponent. The first term is a to the n, and the last one is b to the n. The second term is one less, decreasing the a's and increasing the b's. And then the second one is the reverse of that. The powers decrease by 1, while the powers of b increase by 1, moving left to right. So we sort of talked about that, where I went from x squared to x to the first to x to the 0, and then y to the 0, y1, y squared. And then finally, the sum of the exponents in each term is n. I didn't specifically show you that, but right here, I see right here I've got 2, which is my original exponent. If I add both of these exponents, 1 plus 1 gives me 2, and then finally I've got 2 right there, which is the 2 up there. So the way we can find the coefficients, or the leading parts of this triangle, is using Pascal's triangle. And the way we create this is we add the 2 values that are directly above it. So here, Pascal's triangle, I give you the first 7 rows. The top ones are always 1, 1, 1. And going down the sides, it's always 1. But then to find the values in between, you add the 2 values that are directly above it. So the next row down, we start with a 1. 1 plus 2 is 3. 2 plus 1 is 3. And then a 1 goes on the outside. 1 starts the row. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. Outside is 1. And you looked at that last year, this pattern of Pascal's triangle. The other way you could look at Pascal's triangle is that it's a combination of n choose r. N choose r. Where n is going to be the number of rows, or the row number, and r is going to be the position number. So right here, this n is going to be the row number. The r is going to be the position number. And with both of those, we start from 0. So we count from 0 upwards. So if I were to go with a Pascal's triangle, and I wanted to figure out what is a specific portion of Pascal's triangle, I can look at it from a row and a column perspective, or row and a position perspective. So I'm going to pull out an example of Pascal's triangle here. And here's Pascal's triangle. The very top one is row 0, position 0. So this honeycomb square is 0, choose 0. Here, this one that I've highlighted in yellow is the 8th row and the 3rd position over. So we count from the top 0, 1, 2, 3, 4, 5, 6, 7, 8. So it's going to be 8, choose 2. Row number and position number. This one right here, this 186, is the 13th row and the 3rd position. You might think, well, it's 4 over. Well, the first position is 0, 1, 2, 3. And each individual piece can be found by using N choose R, where N is the row number and then R is the position number. So if I looked at 120 right here, this is the 10th row, so it's going to be 10 choose something, 0, 1, 2, 3, 4, 5, 6, 7. So that would be 10 choose 7 would be that 120 right there. So that's how Pascal's triangle works. There is a formula for N choose R, which is N factorial over R factorial, N minus R factorial. But most of the time, we're just going to use our calculator in order to find these combinations. And where we find the combinations is under math and then probability. You see NCR as being option number 3. So the way we plug into our calculator 5 or 10 choose 5 is we type in a 10. We then go to math, probability, and choose option 4 or 3. And then we'll type in the 5. So there's 10 choose 5, which gives me 252. The next one, 12 choose 4, same idea, 495. Just use our calculators to find those combinations.